So the streaming is on. All right, so what we'll do today is we'll take one last look at carry look-ahead adder, particularly that gigantic and seemingly complex and or expression. So what I'm talking about is here in section 6, and I'm talking about this mess here. Okay, so we'll take a look at this mess, and then I'll try to write a pseudocode thing to basically expand what this is, and I might go through one or two examples just to work out how that thing works. In fact, I think I'm going to choose one or the other. So I will either give you the pseudocode, or I can go through an example so that you guys know how to expand this thing here. Which way do you guys want? Example, or do you want the pseudocode? Okay, I heard example. Okay, we'll go for the example. Because the notation is already telling you what the loop would look like. It's a loop inside a loop. Okay, so let's go ahead and talk about an example. And I do want to emphasize that this class is not an online class. It is not a hybrid class, despite I'm using YouTube to stream the content. So, it is a face-to-face class, and everybody is supposed to be physically here in the classroom as the class is being conducted. So, just want to remind people of that. All right, so what I'll do is I'm going to go try to figure out a particular k. Okay, in other words, I will plug in a particular value for this n, and then we'll see how the expression expands. So are we doing okay so far with that? Yes?
I had one question about the breakdown above this and just section 6.
Okay, let's go back to section 6 a little bit. And which part?
The huge breakdown above this.
This one?
Maybe scroll up.
Oh, the really long derivation? Yeah, what about it?
On the third from the top, where does that 1 come from?
You mean this one?
Yeah.
That is introduced. In other words, true is the identity of conjunction. In other words, it's kind of like multiplication by 1. When you say something and true, you're not changing, the original expression. So, just like in a normal math expression, if you say, x times y, okay, for instance, that's the original expression, you can always just, add a times 1 without changing the meaning or the value of the expression. So that's kind of doing the same thing because, and true, x and true is just x. And we know that because of the truth table. So you can use the truth table to just prove that. I mean, that's one good thing about Boolean algebra is most of the equivalency can be proven by a truth table. So you just look at all the possible cases. If 2 columns look exactly the same, then we're good. So is that kind of explaining, how I can introduce that 1 when it wasn't there to begin with?
It explains it. I'll bring it up when we get to the subtraction part, because I noticed there's a...
Okay. Yeah, the subtraction has a different derivation, but using kind of the same tricks. Okay, all right. So we're going to go back to this thing here. And I'll give you one example. I'll work out, maybe K4, step by step. So that way you can kind of know, how the whole thing works. Okay. And each semester I do this in a slightly different way. So you're welcome to look at all the past lectures of this class and see whether those examples make more sense to you or not. All right. Okay. So I'm just going to put my text editor down here. And instead of using square brackets, for the index, I'm just going to not use the square brackets. So xi is just xi without square brackets, okay? Because otherwise it gets kind of long. Okay. So we want to say what happens when n equals to 3, because we want to figure out what is k4. Okay. If you want to figure out k4, that means 4 equals to n plus 1, which also means that n equals to 3. Okay. So we are trying to figure out the case when n equals to 3. All right. So the outermost thing, is saying, it's a big OR. And the big OR says, I want I to go from 0 to, in this case, we know n is 3, okay? And then we have one kind of gigantic thing over here, plus k0 and then we have a gigantic and here. And that and, has I going from 0 to 3 again, because you can see how right here, I is going from 0 to n, and we know n in this particular example is 3, okay? And then we have pi over here. So do we have any questions about this expression, which is really just the original expression, but with two exceptions? We have kind of like I ignore the big OR for now because I want to focus on the big and on the right-hand side, this guy over here. And then we also know that n has a concrete value of 3. Is that okay so far? Okay. So we'll just deal with that part first. In other words, we'll go like, this part is a little bit complex. We'll leave it alone for now. And now it becomes k0. And then the and is really just saying, give me all the p0 to p3, and then and all of those together. Okay, that's what the big and is doing. Is you just want to figure out what each expression becomes when I becomes 0, when I becomes 1, when I becomes 2, and when I becomes 3. And then with each sub-expression for each specific value of I, you and all of those sub-expressions together. Are we doing okay so far with that concept? Okay, so this becomes just p0, p1, p2, p3, and they're all ended together. So do we have any questions about this step? No questions? Yes?
So the carry upward is and, the carry downward is or. For your notation.
Okay, so if for the notation, okay, this is and this is or. So it really helps to kind of review the material from week 1 because that's something that we introduced kind of early on in the class. So it's really good to kind of get all the previous notes reviewed so that we don't encounter this problem. Okay, so now we deal with the left-hand side, which is kind of messy over here, right? So we'll deal with that. So the way we do that is we basically say, what happens when I equals to 0, okay? So when I equals to 0, then we have g0 times, the big and then this big and has j going from, but in this case, remember, I equals to 0. 0 plus 1 is 1. And then we also go to n is 3, like that. And then we have all the p of j's in this case. Okay, so let me highlight a portion. So this portion is basically corresponding to what goes in, into the gi and then the big end. So this is the highlighted portion is what happens when I equal to 0, just for that one single sub-expression inside the big OR. So are we okay with that? Okay. So this, excuse me, I have to say this entire thing is what happens when I equals to 0. Okay. So I'm going to comment here when I equal to 0. Okay. Then we have when I equal to 1. So we have g1, big and over here. Now what this time, what is the starting point of j when I equals to 1? 2, right? Because I plus 1 is 2 when I equals to 1. So now we have 2 to 3, p of j. Okay, this is when I equals to 1. Yeah, we do. But right now I'm just expanding all of the items. But yes, we do need a plus sign. Then we have g2 because when I equals to 2, this is what we're going to have. J equals to 2 to 3, 3 to 3, pj plus, okay, this is when I equals to 2. And now we have g3 because this is what happens when I equals to 3. Now this one looks kind of funky because j equals to 4 to 3, pj. Okay, so we're going to leave it alone for now, and then we'll figure out what that means later on. Okay. And then we have a final plus of whatever is to the right-hand side of the big plus over here. So for that, we just copy and paste this portion and stash it over here. Do we have any questions about this? Yep.
If I'm reading that right, it's the G of 0 line plus the G of 1 line plus the G of 2 line plus the G of 3 line, then plus K0 line?
Yep. Yep. So those things are all ORed together. Okay, which is kind of the essence of carry look-ahead is you just have a whole bunch of ands, and then the result of all the ands are ORed together. So you only have like 2 levels of gate at this particular in this particular form. Is that okay? Because even without expanding anything, we can see that G0 and a whole bunch of stuff ANDed together, that's just one gigantic AND. So that can be done using a multi-input AND gate, right? And it has one single output. The second line is a little bit smaller, okay? It has one fewer input, but nonetheless, it is an AND gate. Another AND gate, and this one actually is not an AND gate anymore, but I'll explain later. This is another big AND gate. So all of these can be done in parallel, okay? This, and this. They can all be done in parallel. And because the worst case is they need one single AND gate, so it's only 1 unit of propagational delay. And then all the results, okay, 5 results will be available at pretty much the same time, 1, 2, 3, 4, 5. So the results of all of those will then be ORed together in order to give us K4. Is that okay? In fact, accidentally I use a representation where it kind of looks like gates also, because we can see all the ANDs feeding into the OR. Okay, so now we expand everything. Okay, we have G0 over here, and because we are going, J here is going from 1 to 3, and we look at all the PJs, so that's just giving us P1, P2, 3, P3. Okay, so we have an OR. The second line is G1, and J this time is going from 2 to 3, so we only got P2, P3 this time. The next line is when I equals to 2, so in this case G2, and then we only got P3 because the index variable J is going from 3 to 3, so it only goes through 1 iteration. The last one is deceptive because we don't have any P's. That loop did not run because the starting number is already greater than the terminating number. So we don't go through a single iteration. So we don't have any P components. We only got the G3 in that case. And then plus the last one, which is outside of the OR generator thing. So we still have the same K0, P0, all the way up to P3. And we just paste it over here. And that's how we get to K4 using the generator expression. So do we have any questions about this? No questions? All right. Can we kind of see that we have we have several AND gates, and they can all operate at the same time? And then when the result of the AND gates become available, then we can feed all of those to the OR gate, and then the OR gate finishes the entire computation, and then we got K4. Yes? Okay. Great. So this is kind of the explanation of I would just call this the generator expression. Do you think you can write a loop to do this? Yeah, I think it's a double loop, right? Because one loop to iterate through the I values, and then for each I value, you need a second loop to iterate through the J values. So you need a double loop for the left-hand side, and then you just need a single loop on the right-hand side. But nonetheless, we are not talking about anything too complex. It really is just a loop, just 2 loops. Is that okay? So if you do it by hand, yes, it is super tedious. If you want to use Logisim to build the circuit, it's super duper tedious to build something like this. But on the other hand, if you're using a HDL, which is a hardware description language, you can actually specify loops in a hardware description language to generate the actual expression. So that means, hey, if we can do it in a loop, that means you don't have to worry about it. It might crank out something that is really ugly to look at once you look at the circuitry, But from the generation perspective, the algorithm to generate the expression is pretty clean and pretty easy. All right? So in this class, we are not going to play with HDL much. Okay? There will be a little bit of exposure, but not a whole lot. For those of you who plan to transfer to UC Berkeley for their EECS Bachelor of Science degree, then you will have a lot more exposure later on, okay? Because Berkeley is going to teach you how to use, if I remember correctly, Verilog, because there are two main languages for HDL. One is called Verilog, and the other one is called VHDL. I cannot remember which one Berkeley uses, but you'll be designing a processor using those HDLs at Berkeley, and that's one of your final projects for the computer science degree. Okay? All right, so shall we move on to subtraction? Because we are done with addition, unless you guys have questions. Okay, if there are no questions, we're going to move on to subtraction. All right, so subtraction is right here, and we'll take a look at subtraction. So the first thing is, we need to review, adding, and I have just gone through a little bit of that, okay? And I even have a link here, a hyperlink, so if you say, oh, I don't know where to find the addition module when I'm reading the subtraction module, just click that link, okay? That will bring you back to the module that I was just going over. Okay, so section 3 is talking about, okay, if we look at subtraction, there's a result and there's also a borrow instead of a carry, okay? So I'm using base 10 as an example. So I'm asking you, what is 9 minus 2 in base 10? Most people will say, oh, that's easy. That's just 2, right? Okay, that's correct. But what if I ask you about what is 2 minus 9? Well, most people would say negative 7, okay, which is correct. But if you want to carry multi-digit subtraction, then it's better to say 2 minus 9 is a 3 with a borrow of 1. Does that make sense to you? No. You guys have forgotten how to do subtraction by hand entirely because you have calculators now. Tell me that is not the case, because that would be really sad, really, really sad, that you guys cannot remember how to do subtraction anymore. Okay, so let's do subtraction then in base 10, okay? Let's have a quick review of how to do that. So let's just say that we have 129 minus, and this is all in base 10, okay? Minus, we'll just say 72, okay? So you guys do not use a calculator. I want to force you guys to do it by hand, okay? That's the whole point. So we're going to do the same thing, similar to what we did with addition. So we have all of these rows, and most of you will go like, well, but I don't need this many rows in a normal calculation. Well, we're going to do it this way. 9 minus 2 is a 7. This borrow is usually 0 because no one is going to borrow from this digit. It's already the least significant digit. So that borrow is usually assumed to be 0. Is that okay? All right. And I better start to label these rows too. This is x again. This is y again. This is q again. This is now borrow, and I call this t for taking. And then this is the difference, okay? So only the last two rows have a slightly different label, but that's for a good reason. For the most part, okay, it's still kind of the same thing. What is 7 minus 0? Well, that's just 7. So now you have to ask the question, did we borrow anything from the next column? 9 minus 2 didn't need to borrow. 7 minus 0 did not need to borrow. So we don't have to borrow at all from the next column. So that means nobody borrowed from this column. So the borrow from this column is a 0. Is that okay? All right. Then we look at 2 minus 7. We go like, that is going to need to borrow. Okay. So now Okay, this is important because I know you guys remember what borrow means, but what does it do? Okay, that's the important part. Because 2 is less than 7, we cannot do the subtraction. So what we are doing is we are borrowing 1 from the next digit. But when you borrow 1 from the next digit, you are not just borrowing 1, you're actually borrowing 10 in this case. Because in base 10, it goes from 1 to 10 to 100 to 1,000 to 10,000 and so on. So the digit to your left-hand side is 10 times what you are representing. So when you borrow 1 from the next digit, in your perspective, you're borrowing a quantity of 10. Is that okay? So now we have a borrow of 1. Okay, we put a 1 here. So this 2 is now becoming 12 because you just borrowed 10 from the next column. So you have 12. 12 minus 7. We know the answer to that one. It's just 5. Okay? 5 minus 0 is 5 over here. So we got a 5 in this case. This is implicitly a 0, right? 1 minus 0 is a 1. 1 minus 1 is a 0. And there's no overall borrow. We are good. We are not owing anything. Is that okay? Is that reminding you how to do subtraction manually? Okay, good. All right. So we are just going to say the result of a subtraction. So R is kind of redefined now, to represent the partial difference of a subtraction. So I will give you some examples, okay? And I will just say that in base 10, if you subtract a 7 from a 2, then you get 5. Is that okay? Does everybody understand what R means? Okay, R is basically what goes onto the Q row out of, by doing the calculation of xy. It's also what goes onto the D row, after you use Q and T for the subtraction. Okay, so let's use another example. Okay, 1 and 3. Okay, what do you think that is? What is the result of subtracting 3 from 1? We don't want negative. Remember, we use borrow to deal with that negative stuff. So what is 1 minus 3? That really hurts. 1 minus 3. Okay, 1 is less than 3, so the subtraction cannot happen. You have to borrow. After you borrow, you get 11. 11 minus 3 is 8. Okay? There we go. Are we good so far? No? Do we all have to retake remedial math? All right, so now let's deal with borrow, okay? The borrow of 2 minus 7 is 1. We do need to borrow, okay? And the borrow of 1 minus 3 is also 1. Is that okay? Let me just be very sure, okay? What is the result of 3 minus 0? Okay. What is the borrow of 3 minus 0? 0. Very good. Okay, so I think we're getting the hang of what R means and what B means. Are we good? Yes? Can we do another example? How about you tell me what numbers you want to plug in here, and I'll tell you the answer.
Sorry, say that again.
How about you tell me what number you want to plug into these two parameters?
I say 1 and 7.
1 and 7. Okay. So what is the result of 1 minus 7, taking 7 from 1?
4.
4? 4 is correct. Okay, very good. And what is the borrow of subtracting 7 from 1? It's 1, because 1 is less than 7. We have to borrow. Are we doing okay so far? Yes?
I'm making a prediction that the G function is just going to be
Exactly. Yep. Exactly. So if I want to write a C function for R and a C function for B, what will they look like? Okay, so I know most of you have some idea already, but how do you make it as short and as concise as possible? Okay. Okay, let's make them unsigned because that's what we're dealing with here. So R unsigned X, unsigned Y, and what are we returning? I know most of you are thinking, but I need a conditional statement. No, you don't, because we got something called the ternary operator in C. Okay, let's think about the condition first, okay? Because most of you are already thinking, well, but sometimes we need to go this way, and other times we need to go the other way. What is the condition that will send you one way or the other way? Yes, back there.
X is less than y.
If x is less than y, okay, so we know x is less than y is some kind of important condition, right? Okay, so if x is in fact less than y, what should we be returning? No. This is the R function. This is not the B function. Yes?
X times 10 minus y.
Close. Plus. Okay, very good. So we borrow 1 from the next digit, which means I end up having 10 more value, right? My value is now 10 more than before. So we just say that we add it to x. So 10 plus x is guaranteed to be greater than or equal to y. Yeah. Yes. So now we can do the subtraction of y, right? So everything's good. What about the else? What if x is greater than or equal to y? Then we just do the subtraction, right? And we're done. A single return statement. That's all we need. So does anyone want me to review the ternary operator? Okay. I'll give you a 20-second review. This is the condition. This is the, okay, to the left of the question mark is the condition that you need to evaluate. Between the question mark and the colon is what's called the then value. So if the condition is true, this is the value that you want to return as the value of the entire expression. To the right-hand side of the colon is called the else value. That is the value that you return when the condition is the value of the expression to the right-hand side of the colon becomes the value of the entire expression if and only if the condition is false. Okay, that took a little more than 20 seconds. Close. Is that okay? So for those of you who want to look at this, okay, I will do this once in this class because remember, I assume that you guys have taken and passed C++, and this is actually a very useful operator in C++. If you were never introduced to this ternary operator in C or C++, don't blame me. Blame whoever taught you CISP310. And you can quote me. And I usually do not like to use a return in the middle of a conditional statement, but this is one of the few cases where if I don't, it makes it even uglier. Okay, so I'm just going to do it this time. Is that okay? So the two functions are identical in terms of meaning. One is way longer, okay? The other one is not. Yep.
So is the question mark in the colon, is that proper syntax for anything?
Sorry?
Did you actually use the question mark in colon in C?
Yeah. Yep, it's called a ternary operator. It's very commonly used because it saves you the trouble of not having to use a conditional statement, and instead it is the expression that can evaluate a condition and decide which way it needs to go. And it can nest. That's the best part. Okay? Because in a ternary expression, this by itself can be its own little ternary expression, and this by itself can also be its own ternary expression. So you can actually have a decision tree encoded into a single expression. So combining this with recursion, you can do a lot of stuff with a single line, subroutine. All right, so are we okay so far with R, the meaning of the R function? Yes? Okay. What about the B function? Okay, how would you do this? I'm thinking about copy and paste. Yes?
We use the ternary function again.
Yep.
Say return if x is.
Let's use ternary operator because I really want to force you guys to think in ternary operator for a little bit.
X is less than y, return 1, otherwise return 0.
Yep. There you go. That's your borrow. Do we need to borrow? Well, is x less than y? Yes. Okay, then we have a borrow of 1. If not, then we have a borrow of 0. Then somebody's going to be saying, but I have even a better plan because we can do this instead. Okay, so let me see if any one of you is thinking about this because, well, how about just that? It's easy. Why use a ternary operator when you don't need to? Is there a problem? Is there a problem?
Well, that should return Boolean.
It returns, no, well, this is plain C, and plain C has no Boolean, okay? So what is the definition of true in C++ or C? Not 0. That's it, okay? So how many not 0 values do we have in unsigned? A lot, exactly. So it's not guaranteed to be a 1. It's guaranteed not to be 0, but not guaranteed to be a 1. So if you want to force the return value to be either 1 or 0, then you have to force it to be a 1 or 0. Okay? So are we good so far? All right. Cool. Now we're going to look at these as in base 2. Okay? So I'm hoping you're now getting reacquainted with subtraction, the concepts, right? So now we want to think in base 2. And you guys are thinking, oh, no, not base 2 again. No, base 2 is easy. Really, really easy. Okay? And you'll be wondering, why did I learn base 10? It doesn't make sense to me, right? I mean, in base 2. Okay. So in base 2, I will first do the usual subtraction thing, and then we'll turn it into the function representation, okay? So in base 2, 0 minus 0 is what? If I just want to look at the result. It's a trick question. 0 minus 0 is 0 with a borrow of 0. Okay. Is that okay? All right. Because 0 means 0 regardless of the base. If you don't have any money in your pocket, it doesn't matter which country you're in or what currency is used in that country. You have no money. You can say, I have no yens, I have no yuan, I have no US dollars, I have no pesos. It doesn't really matter. You have nothing. You don't have any money in your pocket. How about that? What do you? It's 1 with a borrow of 0 because 1 is greater than 0 and therefore there's no need to borrow. Very good. What about this? 0 with a borrow of 0. Okay. So the only tricky case, because remember, each digit in base 2 can only be a 1 or a 0. We have gone through 75% of all the cases already. This is the last one. 0 minus 1 is what? Okay, let's think about this. Let's think about this. Okay, I need to take 1 away from 0. Okay? And you go like, nope, that cannot be done. Yes, go ahead.
It's 0 with a borrow.
It is no. No. Okay, so let's think about this. Okay, you have nothing. Okay, the bully outside of the classroom is going to ask you for $1. Okay, and you go like, I don't want to get beaten up. So what do? You borrow from somebody, right? But remember, this is base 2. When you borrow from the next digit, you're borrowing 2, okay? You're borrowing twice the value that you are representing, okay? So now you got $2 in your pocket, right? You walk out the door and go like, okay, here's your buck, right? How much do you have left? You got 1, exactly. So 0 minus 1 is 1 with a borrow of 1. Because now you owe somebody $2, okay? Are we okay so far with this? Do you see how the base 10 concept just translates into base 2? The only thing is we can only use 0 or 1 as single digits, okay? That's 1. 2 is when you are borrowing in base 10, you're borrowing 10 each time because that's the reason why it's called base 10. The next digit has 10 times the value of u as a digit. But when you're dealing with base 2, the next digit only has twice the value as u. So when you're borrowing 2. And that's it. That's the only difference between base 10 borrow and base 2 borrow. Are we doing okay? I mean, are we applying the concepts in base 10 but to base 2 this time? Okay, I see thumbs up. Okay, so we can move along. All right, and that's it. How long do you think somebody has to spend to learn subtraction in base 10? You got all those tricky cases: 1 minus 2, 1 minus 3, minus 4, 1 minus 5, 1 minus 6, and so on. Because all of those have borrows, right? And unlike addition, which has symmetry, okay? It is symmetric in addition. Subtraction is not symmetric. 2 minus 3 is not the same thing as 3 minus 2. So there are a lot of entries to memorize in order to master subtraction in base 10. How long do you think it will take to master subtraction in base 2? It will take you a week to master base 2 subtraction, but that's only because your mind has been poisoned by base 10 subtraction already for all these years. So it would take you a week to detox from base 10. But if somebody had no exposure to base 10 and base 2 is the first time they learned about subtraction, they're done. Okay? 15 minutes at the most. We're done. Yeah?
For base 2, you want to write a b, you don't, that condition doesn't really hold, right?
Which?
You kind of have to use not equal to or some.
What? Say that one more time.
To write the borrow function.
The borrow function?
Yeah.
Yeah, this one doesn't work the way it's supposed to because it doesn't guarantee the return value to be a 1 when you do need a borrow.
Yeah, but like you cannot use compare to like less than because you have to.
Yes, you can. You can compare unsigned numbers, right?
For base 2. Yeah, I'm going to rephrase my question.
Okay. All right, but we also want to look at this from the perspective of R and B, right? Okay, so we want to look at R and B, and we're going to borrow or copy and paste whatever we have here. So we'll say, this works in base 10, and let's see what we can do to make it work in base 2. What do you think? How do you make this work in base 2 when x can only be a 0 or 1 and y can only be a 0 or 1? What do you think you have to change? Change the 10 to a 2, exactly. Decimal to binary. Done. And what about the other one? The same, exactly, because we don't need to use the base at all. We just need to say, is digit x less than digit y? If so, we have a borrow of 1. Is that okay? Yes?
Wouldn't it be easier for the R to just say if x and y aren't the same?
Yes. So we're going to get there. Okay. So right now we have borrowed the functions from base 10 just because I was lazy. Okay. I don't want to think about it. I just say The base has changed, so we'll go, we change the 10 to a 2, and we're good, okay? But these are all arithmetic concepts, and we have a problem if we only have to rely on arithmetic concepts, because the whole idea is we want to do this in transistors, okay? So I have to kind of go all the way back to the first class, okay? Using 2p and 2n transistors, we can build a NAND 2 gate, but using NAND 2 gates, we can build all of the other logic gates, okay? We have NOT, and, or, right? So we want to boil everything down to just NOT, and, or, okay? Which also includes exclusive OR and some of the other gates. But we don't want to use arithmetic calculations, okay? We don't want to use subtraction. We don't want to use addition. We just want to use and or not, okay? So now the question is, can we do that? Okay, so now we want to look at these functions, and then what we'll say is we have one column for x, one column for y, one column for r of xy, and one column for borrow of xy. And then we'll populate this table and then see if we can see a pattern. Yes?
Sorry, I was staring at the table you made.
Which one?
With
The-
the minus 1 minus. Is the minus sign expressed as exclusive and?
No, minus here is really just subtraction. It's arithmetic subtraction. Okay? All right, so let's just plug the values in, 0, 0, 0, 1, 1, 0, and 1, 1, okay? Can someone tell me what is here? What is the result of 0 minus 0, which you can look up here. There we go. All right, so can someone tell me what is rxy when x is 0 and y is 0? 0, and the b is 0, okay? So 0 minus 1 has a result of 1, but it also has a borrow of 1. 1 minus 0 has a result of 1, but it has a borrow of 0. And then 1 minus 1 has a result of 0, but it also has a borrow of 0. Are we good so far? Yeah? Okay. So we want to look at the R column first, okay? Forget about the B column, look at R, X, Y first. Does that look familiar to you? I'm glad you guys say that, because if you say no, then I will go like, you have to review binary addition, because that's the same result as addition. Do we know how to do that one using logic gates? Okay, we already know. Fine, good. What about the B column? The B column looks a little bit awkward, right? I mean, I don't think we have a single operator, as a Boolean operator that can do this, because the only time b of xy is a 1 is when x is a 0 and y is a 1. How can we make that happen? Okay, so R is really the same as before. I can just kind of reiterate what we had before. So this time, oops. So this time, these are logical operations. So what you see as multiplication is really a conjunction. Exclamation point is logical negation, and then the plus is disjunction, which is OR. Okay, but that's the same as before. That's the same as addition. Yes.
So I'm just saying for B, can we just say so x not y or not x y?
There's
Not x.
well.
We just do the R function and not x.
Right, but there's only one row that needs to have a 1, right? So we just need to look at this row and say, what is the simplest expression that can give me a 1 when x is false and y is true? Not x and y. If you have not x and y, then when x is false, you have true, and then when y is true, then you also have true, then you have true and true. That's the only time that this expression will give you a true. For everything else, it's going to give you false. So this will get the job done. Okay? So compared to addition, it's not quite as neat, because addition doesn't have this negation of x. Right? It's just x and y to calculate our carry. But for borrow, we have to negate x first before we end it with y. But nonetheless, it is still not too big of a deal, because it's just having one additional negation for x. Are we good? Are we doing okay so far with this? Good? Okay. So with all of this stuff here, we can now look at a multi-digit subtraction, and we want to figure out, how all those bits, work out. Okay. So I'm going to throw this out again. We got x3, x2, x1, x0. Those are individual bits of x. And then we have y2, y1, and then y0. Those are the individual bits of y. And this particular row, I will call these our q's. So we got q2, q1, and q0. Now do you see why I named that row q again? Because we use the same R function to calculate that particular row. That's why I used the same name Q. Okay. This row is called T, or for take, which is borrowing. So this is T3, T2, T1, and T0 is usually assumed a 0. So we can put a 0 here for now. And then this is the difference. So D2, D1, and D0. Okay. Now I want to know how they relate to each other. Okay. So Q of I is what? Xi, yi. Okay, that's not too bad, right? How about Di? Yep. So R of Q0, Qi, Ti. Okay. Hey, that's not too bad. What about T of I plus 1? Remember K of I plus 1 for carry? This one is kind of very similar, except instead of carry, we got borrow. So if you remember how we do K subscript I plus 1, this looks almost exactly the same, except instead of referring to carry, it refers to borrow. Is that okay? So let's see how we can end up with a borrow. Okay, so let's look at T2. Okay, so who can contribute 1 to T2? In other words, what reasons do I have to borrow from this particular column? X1 is less than Y1, right? That would trigger a borrow from T2. What about Q1 minus T1? That can also give me a borrow. So we got two reasons to end up with borrow from the next digit, just like we have two reasons to have a carry of 1 in addition. So it's really the same logic. Okay?
Is it just like addition not going to be possible to have?
Yep. So it's xiyi, the borrow of that. Now this time I'm going to use arithmetic plus, okay? And then we'll figure out, can we replace it with an or? And then we have qi and then ti. Okay. All right. So this is basically arithmetic. Okay. And I'm gonna make it clear that this is arithmetic plus. Okay. So right now that plus sign really means a plus. And we look at this and go like, nah, I don't like that because I want it to be a logic gate. So now the question is, can I replace this plus with an or? Okay. And the same question, same as last time, is basically, can we have this borrow being a 1 and also this borrow being a 1 at the same time? What do you think? Okay, so what you need to do is to evaluate what happens when 1 is a 1. Okay, so if you say, b of xiyi is a 1, okay, let's assume that one is a 1. And then we'll see what happens to the other borrow. Is that okay? Okay, so what does this imply? If xi minus yi has a borrow, that means only one thing, right? Because this means that xi has to be 0 and yi has to be a 1, right? Yeah. But it also means, qi, which is the r of xiyi, to be what? It has to be a 1, okay? But this also means, the borrow of the borrow of qi ti has to be a 0. Yep, because qi is a 1 already. If qi is a 1, the borrow sets will first negate it. If qi is a 1 and we negate it, it becomes false. And then false and whatever ti is always false. It doesn't matter what ti is. Okay? Right. Well, that only goes in one direction. Now we have to go the opposite direction. Yeah. So we have to look at the opposite direction and say, okay, what if the borrow of qi is known to be a 1? What does that imply? Well, that implies that qi has to be a 0, and it implies ti has to be a 1. Right? Because that's the only time, okay? That's the only time when the borrow is a 1, when we have qi minus ti. Okay, so if qi is a 0, what does it mean? When qi is a 0, what does it mean in terms of xi, yi? They have to be the same. They have to be the same. So that means this implies xi equals yi, right? But what does that? Exactly. That means the borrow of xi, yi has to be a 0. All right? So now we have if and only if. Okay? This goes in one direction. This goes in the opposite direction. So by these two lines of reasoning, we know that these two borrows cannot be 1s at the same time. Now, can they be 0s at the same time? Oh, yeah. Can one of them be a 1 and the other one being a 0? Yes. But they cannot be both be 1s. So if they cannot both be 1s, then we can go back here and say, we really don't need to use a plus here. We can just use an or, which is great because now we know how to do it using transistors. Say again? So, shall we move on? All right. So some of these reasonings, if it is not entirely clear to you in class, you have to kind of review it. Okay. Does it mean that I'm going to put something like this in a test? No, not necessarily. But I do want you guys to go through the reasoning because it is not about what content or what material I teach in the class. Okay? Most of that material is not going to be relevant to what you do when you're at work. It is the reasoning that matters more. Okay? So if I can teach you guys how to reason things out, how to prove something, okay, that is worth a lot more than teaching you actually knowledge. Knowledge is easy. You go to Wikipedia, spend a few days, and you learn a lot of stuff. Okay, so if this is all done, okay, then I think we have almost everything figured out except for, we got D figured out. So we expressed, so right here, you can see how we express all the QIs using xi, yi, using R as a function. We express all the DIs using just QI and TI. And then we express all the T's using the borrow of xi, yi and the borrow of QI, TI. So we have kind of the same structure as addition. Okay? So yes, you can make a borrow ripple subtractor, just like we can use a carry ripple adder. Okay? And they will look very similar in terms of structure. The only difference is a negation. If you go back to the slide, if you go back to the Logisim circuit for the carry ripple adder, you go into the half adder, you put one negation in front of the conjunction. You have to pick the right one, okay? Then the whole thing becomes a subtractor. It's that simple. But what about borrow look ahead? Okay? Because we talked about carry look ahead. So now we have borrow look ahead. In other words, we don't like to ripple the flag, just like we did not like to ripple the carry flag. So the question now is can we remove that dependency? The dependency is actually visible here. You can see how ti plus 1 depends on ti. So we kind of have the same issue as last time. Okay? T3 depends on T2, T2 depends on T1, and T1 depends on T0. That becomes a linear dependency, And that means it's going to take a long time before you can get to T64, for instance. Okay, so we want to see if we can apply the same trick as last time, and we would end up with a borrow look ahead mechanism. Okay, so I have just kind of gone through all the notes, all the way up to here. So this is the part when we go like, okay, so let's look at some Boolean algebra stuff and see where this is gonna go. So I hope the first line does not surprise anyone, because you just saw that from mousepad earlier, except I use an uppercase B on mousepad, and now I'm using a lowercase b. Okay, it's just the case is different. Okay, the second row is just expanding the b function. Okay, negate the first one and the second one. Okay. This one here is just expanding Q of I. So Q of I is the exclusive OR between x and y, and this is kind of the long way to say exclusive OR. Okay? But that's the same trick that we already used in addition. So from here to here, I'm using, this one is new. Okay? From here to here, I use De Morgan's law. And I have not, I don't think I have, well, I think I have introduced De Morgan's law, but it doesn't hurt to introduce it again. Okay? So this is De Morgan's law. Okay. So if you look at De Morgan's law, okay, it says something like this. If you have a negation of A or B, it really is the same thing as not A and not B. On the other hand, if you have a negation of A and B, it really is saying the same thing as not A or not B. Okay. Now, if you look up De Morgan's law, okay, you can get the same thing. Once again, this is just knowledge. Okay, it's not really that important because you can look it up. The question is, how do you convince yourself that De Morgan's law is right? Go ahead. Truth table, right? So how do you use a truth table to convince yourself that these equalities actually hold? So what you do is you have A, B as two separate columns. Then you have one expression that you want to, that is under consideration as the third column. And then you have the other expression that you are evaluating as your last column. Okay, so now you have a 4-column truth table. A and B are independent variables, which means each one can be a true or a false independent to the other one. So you end up with the usual pattern, okay? False, 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 true, true, false, and then true, true, okay? And that's it. This is the beauty of Boolean algebra, is each variable can only be a true or a false. Unlike normal algebra where a variable can be any value, right? This can only be one or the other. So now we have enumerated all the possible choices for A and B. So we look at the negation of A or B. Well, it's easier to look at just or and then we negate it, right? So you already know the only time you have a 0 in the or is when both are zeros. So this is the only time when A or B and the negation of that is a 1. For everything else, those are all going to be zeros. Does that make sense? Okay. And now you look at the other one. Okay. Not A and not B. In this case, it's going to be a 1 because not A is true, not B is true, true and true is true. For all of the other ones, at least one of those is going to be false because at least one of A or B is going to be a 1. So the negation of that is going to be false. In a conjunction, if one side is false, the whole thing is going to be false. So we know for the rest of the rows, the 4th column are going to get zeros. So now you look at this, you look at one expression, you look at the other expression. If they have the same value for each row, then the two expressions are equivalent. And that's it. There's no trick, there's no derivation. It's really just looking up a table and look at the two columns and say, hey, these two columns are the same. Then the expressions corresponding to those two columns are considered equivalent. Is that okay? Now this is important, okay? De Morgan's law itself is important, but you can look it up. But how do you convince yourself that it works correctly is even more important. And then there's something that's even more important than more important. It is having the mindset to question it. And I'm not kidding, okay? I'm not kidding you, okay? Having the mindset to look at De Morgan's law and say, well, I know how it is defined, but how do I know De Morgan's law is right? Having that question in your mind, is important. Unfortunately, that is not something I can teach. I can only, emphasize what is important, but it is up to each individual to prioritize, to find out, okay, what is important to you. Okay? All right? So I can only say what is important to me when I look at something like this. All right. So getting back to the equation thing. So this is the application of De Morgan's law. Going from here to here is the application of De Morgan's law. It looks really ugly because this is basically our A and this is basically our B. So we have the negation of an OR. So it turns into the negation of the first thing and the negation of the second thing. Okay, so it takes a little bit of time to apply De Morgan's law to recognize which portion is A and which portion is B, but nonetheless, it is just an application of De Morgan's law. So De Morgan's law is also interesting in a way because you can see how it is kind of like distributing the negation into the inside, right? Because originally we have a negation to the outermost operator, which is the OR. Now we have a negation to something here. The overall operator, which is an AND, does not have a negation after that anymore. So you can kind of look at De Morgan's law as a way to move negation into the sub-expressions. Okay, now that can become useful later on. Okay, in week, I would say 13 or 14 or so, we'll see De Morgan's law again, but in that context, it's actually even more useful than it is now. Okay, so we apply De Morgan's law again. So this time we take this, and it turns into this, and then we take this, and it turns into that. So we basically just apply De Morgan's law twice, okay, until we have all the negations moved all the way in, and they only apply to x or y. Okay, that's the general idea. And then from here to here is just distribution, okay? And then from here to here is because the negation of x and x is going to be false. Because they are negations of each other, one is guaranteed to be a false. Well, in a conjunction, if one is guaranteed to be false, the entire conjunction is guaranteed to be false. Is that okay? So the zeros get simplified out because false or something is always that something. So that's why the zeros basically disappeared. I introduce a 1 over here, and then the 1 gets even longer, and then I get expressions to kind of distribute it a little bit, and then I factor over here, and once I factor, I extract the y and not y, y or not y, which is always a 1. Yep.
So when you introduce the 1, where do the 2 TIs come from?
The 2 TIs? Because you can OR something, you can OR as many things as you want after a true. It will still be true. So you can say, you can expand it even further, but I only need the 2 i's, the 2 TIs in order to do the distribution for what I need. Yep.
So then if you solving that out, where does the intuition come from to introduce those 2 TIs versus anything else in the board?
That is a very good question that is really hard to answer. Because the question is, how did I come up with this proof? When I go from one step to the next, what do I kind of have what I want to simplify in mind, and I'm just, sometimes you have to kind of like, generate and test, okay? So you try this, see if it goes in the direction that you want. No, it doesn't go in the direction you want, you try something else. But there are certain tools, certain things that you can do in Boolean algebra that you do not have in normal algebra. So the first thing is you have to kind of get used to it. Then you can say, oh, okay, so in addition to a hammer, I also got a screwdriver. But it's hard to describe that process. I can only say that you kind of know where you're going, and then you want to see if you can move terms around to simplify and group certain things together. That would be the best way I can describe it right now. So anyway, and by the way, this may not be the most efficient proof, okay? Some of you may end up going like, hey, I can prove this in fewer lines of steps. Great, okay? Nothing wrong with that, okay? All right, but the final result is this, okay? You look at this and go like, we didn't quite solve the original problem. In other words, ti plus 1 is still depending on ti, okay? On the other hand, if I redefine gi like this and I redefine pi like this, we are looking at something that looks awfully familiar, okay? Because in addition, the only difference between this and the equation for addition is in addition we have k instead of t. That's it. So that means all the derivation that we did for addition would still work here. We just have to replace all the k's for carries to t's for takes. Okay? So I hope that looks kind of familiar to you now. We just spent, half an hour or so talking about it at the beginning of the class. You go like, wait, we have seen this. And it looks exactly the same. So when you already have the p's and the g's, the circuitry to compute sum and the circuitry to compute difference are actually the same. The only difference is how you define p and g. That's it. So if you go back to how we define p and g, you can see how we define g over here and how we define p over here. How is that different from the definitions of p and g for addition? X is negated. That's it. That's the only difference. Yep, just throw a negation to x for subtraction. Do not use the negation for addition. Use a negation for subtraction. So once you have built, okay, so tonight's lab is the second part of carry look ahead, okay? So once again, I think you're done with K1, K2, and K3, those subcircuits. Those can be reused for subtraction because they already assume that you have p's and g's computed. If you have the p's and g's computed, the circuitry to compute k and the circuitry to compute t are identical. You can reuse the complex part of carry look ahead. The only part that you cannot easily reuse is how you come up with the p's and the g's. And the only difference is you have to negate x first for subtraction. That's it. Are we doing okay so far with this? So turning an adder into a subtractor is as simple as just specifying, should I negate x or not? Let's see, what time do we have? We still got 12 minutes left. So I'm going to pause a little bit and see if anyone has any questions about binary subtraction and the similarity between addition and subtraction. Yep.
I just wanted to clarify the reason that formula goes to the same thing is because even though G and P are different, it's still. So basically, I'm just not 100% sure why that formula still gets the same result even though G and P are different.
Because the derivation of K1, K2, and K3 did not depend on how P and G are defined. So there's no mentioning of how P and G are defined. We just look at this kind of recursive definition here. This is the generator. This is the engine that generates all the terms. So as long as the engine to generate all the terms has this particular structure of t I plus 1 or something I plus 1 is defined as g of I or p of I and ti, as long as that structure stays the same, it will still end up with this structure here. Yep.
When's our first test?
It's in the syllabus. So does anyone remember from the syllabus when the first exam is going to be? Well, OK, here's a cue. There are 3 exams in this class. So when do you think the first exam is going to be? About 1/3 through the semester. All right. So are there any questions about addition or subtraction? No questions? OK, so before I end the lecture, did I remember to turn on the recorder? Yes, OK. Yeah, that's kind of the thing that I do, forgetting to click that button, having everything set up, and then forgetting to press a button. OK, so let's go back to the outline of the class, OK? Because I do want you to know where we are in terms of the modules. So what we'll do tonight in the lab is part 2 of the carry look-ahead mechanism. And this is how you turn in the file, which I have to reset the date, OK? So I'm going to open up this lab for tonight. So you'll be finishing up the carry look-ahead mechanism. And you can test it. You can see whether your addition works or not, OK? The next module that we'll be talking about is signed value representation. So we are basically we'll be talking about signed versus unsigned. In other words, well, we kind of know how binary numbers work, right? So just to give you a preview, because we got about 8 minutes left, so I do want to give you a preview of what we'll be talking about. So let's look at a 4-bit number. Okay, we'll say, in fact, let's not do it as a number. This is the one part of the class when I kind of need to draw pictures. Yes. Oh, is not working?
It wasn't working. I don't know if that was.
You are correct. Darn it. OK, so let me fix that first. Because I consolidated my server. So this server is, this is the wrong node. This is the one. Yeah, signed value representation is the one that we want to correct. So if something doesn't work, you just have to change the first part to this. I'll send you guys the instructions to do it too. So we change it to power.arc.losrios.edu and then tilde AUYUNT, and then it will work again. Binary number subtraction, signed value. OK, let me check. Yep, so it works now. I'm going to fix the other one, but thank you for letting me know. OK. All right, so getting back to what I want to talk about. OK, we go to accessory, go to Zerno. OK. So this is kind of my replacement of using the whiteboard, because I can draw here, and everything that is on the screen is recorded. So this is recorded as well. OK. So let's consider 4-bit numbers. OK, so we have only 4 binary digits. Each binary digit can only be a 0 or 1. How many unique values can we represent? How many unique permutations do we have for those 0s and 1s? The first digit can be a 0 or 1. While the first digit is a 0, the second digit can also be a 0 or 1. When the first and the second digits are zeros, the third digit can also be a 0 or 1, and so on. So how many combinations of 0s and 1s are we talking about? OK, so this is the visual way to look at this. This is where we start. OK, the first digit can be a 0 or 1. Look at it as a tree. OK, yep, 16, exactly, because the second digit can be a 0 or 1, can be a 0 or 1. The third digit can also split like that. And then the last digit, the fourth digit, can also split like that. So that's why you end up with 14 possible zeros, combinations of 4 zeros and 1s. Or 4 digits, each one can be a 0 or 1. Is that OK? So that's one way to look at it. OK, for those of you who are visual, this is one way to visually understand why there are 16-bit patterns when you have 4 bits. There's 16 patterns. Okay? So let's go ahead and look at all those patterns. Okay? And this time we'll look at the patterns, but in a circle. I know you guys are accustomed to the concept of a number line, but in this class, we look at number circles, not a number line. Okay? So 16 is kind of easy to work with. Okay. So we got 0, 0, 0, 0 here, 0, 0, 0, 1, 0, 0, 1, 0. I'm just counting in base 2. 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. So I just counted, to all the bit patterns when I only have 4 bits. Okay. So now I want to assign values. Okay. Now remember, these are just bit patterns. Okay. What makes you think that 0, 1, 0, 0 should be interpreted as a number? If I did not say that to interpret it as a number, 0, 1, 0, 0 can literally just means I want this pixel to be dark, this pixel to be lit, this pixel to be dark, that pixel to be dark. So if I don't tell you that to interpret it as a number, as a value, it doesn't have to represent a value. It can represent pixels. It can represent a whole bunch of other things that has nothing to do with values. Okay? But if I do want to interpret each bit pattern as a value, that's pretty easy. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Is that okay so far? Okay. So you can also look at this and say, if I want to do addition, that means I am just moving my hand clockwise. If I want to do subtraction, I'm moving my hand counterclockwise, right? So let's take 3 plus 2, okay? Where's 3? 3 is right here. So if I say plus 2, I just want to move my hand clockwise twice. And that's 5. That works, right? Counterclockwise works too, because if I want to do subtraction, let's start with 12, okay? And we say, what is 12 minus 3? This is 12. If I want to subtract 3, I rotate counterclockwise 3 times, or 3 clicks. So we have 1, 2, 3. Okay, 12 minus 3 is 9. Everything seems to work, right? And if you look at this wheel and say, but Tech, I really need to represent values that are negative. Okay? So if you need to look at this and say, I need to represent values that are negative, which one do you think makes sense to represent negative 1? In other words, I say, here's 0. Let's subtract 1 from 0. I should end up there. So which bit pattern do you think should be the one representing the value of negative 1? Okay, so here's 0. Moving counterclockwise is subtraction, right? So I subtract 1, click. Oh, so that means 1, 1, 1, 1 as a bit pattern is the one that makes sense. If I need 1 to represent negative 1, it should be 1, 1, 1, 1. Is that okay? So that means, okay, using a different color, this, oops. So 1, 1, 1, 1 can also represent negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, and negative 8. So you look at the ones that have 2 interpretations. The first question is, how do I know which way, right? Because you look at one particular bit pattern, let's say 1, 0, 1, 1. Then the question is, should I look at this as 11 or should I look at this as negative 5? Right? So let me ask you a slightly different question. Why do you care? I mean, literally, why do you care? When do you need to care whether 1101, 1011 is representing -5 or 11. Why do you care?
When you're computing arithmetic.
What kind of arithmetic? Hmm? They work the same way in terms of addition and subtraction. Hmm? Two's complement is the same thing as negation, arithmetic negation. So if you give me the representation of -3, I can figure out the representation of 3 and vice versa. That's what two's complement is doing. So the question is, why do you care what is the value represented by a particular bit pattern? That is the question. Why do you care? They work the same way in an adder. They work the same way in a subtractor. So why do you care? There's only one kind of operation in a C program where signed versus unsigned makes a difference. Comparison, very good. Okay, so comparison makes a difference. So if I say, okay, let's look at the bit pattern 0, 0, 0, 0, okay? And I'm asking you, is 0, 0, 0, 0 less than 1, 1, 0, 1, okay? Now you have to ask, so should I look at 1101 as a signed number, in which case it will be representing 3, or should I look at this as an unsigned value, in which case it will be representing 13, because the answer will be different. 0 is less than -3 is false. 0 is less than 13 is true. That is the only time it actually makes a difference. What about adding and subtracting? It doesn't make a difference. Because 1100 plus 0001 is always going to be 1101. And it works whether it is signed or not. So addition and subtraction, it doesn't really matter. Okay? You don't need to care whether the bit patterns should be interpreted signed or not. It is only when you need to find out the ordering, which one is less than which one, then it matters. Okay? So this mindset is entirely different from what you have learned in C and C++. Because in C and C++, the first thing you do is what? You declare the type of your integer. You have to decide, is it signed or unsigned? In assembly language programming, we don't care. We don't give it a bit until we have to look at the result of a comparison. Then we have to be careful and go like, okay, let's be sure that is it signed or is it not signed. That's the only time. Okay. So I'm gonna leave this here. This is the last portion of today's lecture. But what you need to do is to at least catch up with the notes as far as what we have talked about in class. But I think it will be very helpful if you can read ahead of me, because these concepts can be a little bit confusing. The symbols, the equations, the expressions can all be confusing if you don't have a little bit of pre-exposure before class. So you have been warned.